Okay, so what we're looking at is problem 4, page 50. Again, I'll just state the problem. A 100 volt voltage is 60 degrees out of phase with another 100 volt voltage. Find the phasor sum. First of all, what if the two voltages were 180 degrees out of phase with each other? What?
Just like flat line?
Yeah, just a flat line. Yeah, exactly. It'd be a zero. You get nothing out of it. Also, what's the main reason for having three-phase power?
It converts better to DC. Says it is not.
Maybe that might be one reason.
More efficient.
Yeah, it's a little, the way an easy way for me to think about it is, well, look at your six-cylinder engine, for example, in your car. I mean, the reason for having a multi-cylinder engine in your car is so, and if you look down that camshaft, each of those cams is out of phase with each other. And if designed properly, at six-cylinder, you're going to have a pair of them that are actually 180 degrees out of phase. One's up while the other one's down. But if you go down the line of those other two pair, ideally they're actually going to be 60 degrees out of phase with each other. So the idea is something's always pushing. That's the idea behind having three-phase. It's something's always. Now you could do two-phase, you could do two-phase where everything's sort of 90 degrees out of phase, but it's not.
Really wouldn't work.
No, it doesn't work as well. In fact, I played a prank on.
Keystroke motor mix.
Yeah, I played a prank on one of my fraternity brothers and stuck his two pedals at 90 degrees to each other. You get the square cranks on the bottom bracket. So he stuck, and he was in a rush to get to class. He pedaled it, but it was not very efficient to be 90 degrees out of phase with the two leg. But that's the way I usually look at it. And the same thing even with this wind turbine behind us. It's got the three blades there. Sure, you could do two. Sure, you could do four. But it just balances out. Three is just a nice number. Okay, so here's the math behind this phasor problem. And this is similar to that RMS value we were talking about a little bit before, Ryan. Because with your AC voltage, during part of that cycle, during part of that phase, you actually don't have any voltage at all. It's not doing a dang thing. It's just sloshing back and forth. That's why the RMS is important. That's why the average is important. And this 60 degrees is critical to getting that three-phase power. It's 1/3 of 180 is all it is. Okay, so here's the math and the terminology behind it. Now, the voltage, and this is just V1, I named it V1 because that's given a 100 volt voltage, 60 out of phase with the other one. Doesn't really matter which one's V1 or V2. It's probably not even going to matter whether this 60 is positive or negative. You could run it both ways just to make sure. But the important thing to note is that one of the voltages is 60 degrees out of phase with the other one. Now, what's this omega thing?
Resistance?
What's that omega? What's that funny looking W?
That's angular velocity.
If this were a mechanical system, it would be angular velocity. In an electrical system, it's called the frequency. And what are the units of omega? What's it measured in?
If it's frequency, wouldn't it be hertz?
It's measured in hertz, exactly. It's measured in hertz. That's the same as 1 over seconds. So, should be able to see now, if I multiply something that's 1 over seconds by time, which is measured in seconds, I have something that's dimensionless. It's just a number. And you guys do that all day long in trig. You're taking the sine of some angle. In this case, we've got the thing written in degrees. What's 60 degrees in radians? About. This is something like maybe if you stayed awake late at night thinking about trig, you might just kind of know the answer to that. But again, just kind of making conversation here.
Pi over 3.
This is like Bee Gees lyrics. I don't know why I know what the number is, but this is like the song that's stuck in your head. Just the stupid junk I remember. How many radians is 60 degrees?
It'd be pi over 3.
I got pi over 3. Jesse's working on the exact number. We'll come up with that in a second. I'll run it through. I'll run it through Excel really quick too.
Yeah, 1.047.
Yeah. So let's just do 60. Up here you can do equals radians of that number. You got 1.047. Yeah, it's about 1. 1.047, which is approximately 1. A radian is about 57 degrees. And the way to think about it is that if you're going from 0 to 180 on your unit circle, or if you're going from 0 to pi, and you know that pi is about 3, 60 degrees is about a radian. That's all I was looking for. Okay. Now we know what the sine function looks like. What's this thing called? What's V naught called? Any idea? That's just called the amplitude of the function. It's how big it is. So all this stuff over here is just telling you how it jiggles. That's all it does. It just tells you how the thing wiggles, and it wiggles in a sine wave. These two guys just tell you how big it is. So if so the way to think about it is just that right there is your V naught. You're just measuring it, and that thing right there is your frequency. So frequency goes up, the peaks get closer together, right? Because it's 1 over time. Amplitude goes up, the thing gets taller. So those two numbers, the amplitude and the frequency, dictate that form. You can kind of think of it like height and width of a rectangle. But those are really the only two things that dictate that shape. You've heard about AM radio. The signal gets by making the amplitude bigger, but the frequency stays the same. You've heard about FM radio. That's just changing that frequency a little bit. So there's only two things to play with in any of these signals. In this case, we're doing power instead of signaling, but same principles apply. Okay, now phasor sum. All right. Here is the diagram that we're going to work with. V1 is 100 units long. We just made it, we just drew it flat on the, flat on the horizontal. The V2, I wrote right here, got a little bit garbled, but it's pointing in this direction. There's your 60. Now, why did I draw it like that? Why is it kind of pointing up to the right instead of up to the left? Why did the 60 get drawn where it did instead of on the other side?
Reference? Anything?
It's definitely a reference, but reference to what, though? And this is something, because it's not just arbitrary, this is something that's, critical. I just looked at this for the first time in a couple of, well, I can't really remember. But if you go back, go ahead, tell me.
Well, no, I'm just saying that the reason why you put the 60 there.
I mean, I know the book tells you to.
Yeah, well, yeah, but.
But I also want us, to be able to get this in our own head so
If
that.
you're using sign, is it sign that has, you can only be positive or negative 90 to get the outcome? And then you have to use cosine, right? Or am I thinking about that opposite?
Well, no.
Because one only goes to positive 90 and negative 90 in your reference circle. Else you have to use a different sign, like cosine. I know.
We'll hit that in a second. That'll be a good review for us, sine and cosine. The reason that the reason that this arrow is pointing the way it was and not, well, if there were 0 degrees between the two things, it'd be right there. There's 0 degrees between that V1 100 that was there previously and that red that I drew. They would be in phase, pointing the same direction, and you'd have double the amplitude. Does that make sense? Now, if I take it, let's just take it 5 degrees out of phase. Not too bad, but I've got less amplitude. There's our 60. Let's take it 90 degrees out of phase. It's not really helping us at all, is it? Like we talked about just a second ago. It's like me futzing with my buddy's bicycle. Now, if we take it 180 degrees out of phase, and I think we just talked about that too, and Jesse said correctly, they're working against each other and you got nothing. You add those two vectors together and you're back to 0. So that's why the 60 is pointing in the direction that it is. Is that clear? So I showed you where 0 was, and they're working together. It's like, two people pulling a rope together or parallel motors working together. And I took it 60 degrees out of phase. Now there's going to be another one. Well, let's just worry about these for now. But, so the point is, what I'm looking for is the phasor sum. Is that actually the answer? Phasor sums. V1, 2. Oh. I think that's just the answer. I didn't write the number in there. Okay, but let's get to why this is actually 50. Yeah. Okay. So what I've got this first triangle over here. So I know that if I got 60 degrees here to get all the way there, it's 180 total, so that thing's got to be 120. You guys know that from trig. If this is 120 and that line there is equal to that line there, if they're both 100, I know I've got an isosceles triangle, And the two opposite angles have to be the same too. So there's, out of 120 degrees, there's 180 to go around within the triangle. So you got to split the remainder half and half. So you just got 30 each. Is that clear? So 180 inside. So there's your 180 right here, your 180 right there, there, and there. So now we've built that guy. The phasor sum is really just no more than the vector addition. You're just adding this vector to this vector. Just add them together. And the way you add vectors is you put the root of one on the head of the other and just follow your, here's your start, here's your finish. What's the quicker way to get there? Well, would just be to go straight, if you could. Okay, so V12 is what I'm just calling the vector sum. So how do we get the length of that angle? I took a little shortcut, took a little trick, because I can see right here that I do have a right angle. And in that right angle, what's the name of that line that I just drew? That's the hypotenuse, perfect. And I already know, so I know one angle, I know 90, I know 60, and I know the hypotenuse. If I know three things about a triangle, I know everything, right? There's my three things. Oops. So from there, just looking for the height, because I know if I can get this height right here, then I've got another right triangle waiting for me. So this height is just equal to the hypotenuse. There's my 100. That was my V2 all along. Minus the 50. Well, where the heck did the 50 come from? Let's check it out. Let's check that out. So if this side is, maybe I'll go back to red. This side is C, this side is A, and this side is B. What I'm looking for is A. And so I know that that's 30. There's a couple different ways to do it, but I know that A equals C times sine of 30, or A equals C times cosine of 60. It better be the same thing all day long. Let's just double check. Let's just double check. So we got, here's our 100. And again, that's called the amplitude. And let's do our cos here. Let's do our sine here. And I'm just going to pop in 30 first. No, I'll pop in 60 here. I'll pop in 30 here. Now I'm just going to kind of play dumb and try to find A equals amplitude times cos number. And let's do it again over here, because I know they got to be the same. I'll do it one more time. Oh, let's do it right here. Equals amplitude times sine 30. Whoa.
You put K2 instead of K3.
Oh, thanks. I knew I was wrong, but I didn't think I was that wrong. Now, are those two numbers the same? No, what did I do wrong here? Why did that not work?
Should be 100 sine 30 in each 50, and then 100 cos 60 in each 50.
Well, let's check it out. I'm going to convert to radians first. And this is going to be, I'll just call this first try right here, which is what I just did. And I know that that formula in red, A equals C sine 30, A equals C cos 60, should be the same thing, but they're not. And the reason is this, A equals, let's try it one more time, amplitude times cos, and now I'll use the radians number I just calculated, equals, I'll hit K3 this time, times sine, I'll use the radians. Boom. So Excel needs you to give the arguments in radians. So I took my, just to review, I took my 60 and my 30, converted them to radians just below. Radians just below. And then used those, so my first try was wrong, because you can see I just stuck in the degrees, didn't work. But once I put it in radians, no problem. 50. There's my 50. Now I know that the base down here, the length of this guy is 150. I just add them up, straight up. There's my 150. The 86.6 was H or B, same thing. It's that third leg we haven't really talked much about. And well, that was the height. And now to get the length of V12, let's just pop it in really quick. Equals SQRT, open paren, 150 times 150 plus 86.6 times 86.6, close paren, 173. So that's the kind of the most expeditious way to find that that phasor sum. And the point is, now you've got 170, what is that, 173 volts to play with. It's a more powerful system than just your single phase guy. All right, so I think that's probably, those are the two most critical things to cover for 213. Knowing your transformers, the physics of it, the math of it. Same thing here. I think we talked about the physics of phasor sums, why you use a three-phase circuit, applied some trig. Hope you saw that little trick. You saw the reason for why that 60 points in the direction it does and not any other way. So I'm adding them 60 degrees out of phase, not 0, not 180, but 60. That's why that's the way it is. I showed you the geometry behind the amplitude and the frequency of a sine wave or a cosine wave. Does it really matter if you're talking about a cosine wave or a sine wave?
Well, yeah, because cosine and sine is just x out of decimal.
It does if you're adding them together. But here's another thing that you want to look at on this guy. With sine, this is 0, this is 1, this is 0, and down here is -1. and I'll do a different color. Cosine, this is 1, this is 0, this is -1, and this is 0. So back to your question a second ago, sine and cosine take on all values between 0 and 1. They're just 90 degrees out of phase.
They're bad at math, but this is much easier.
Okay.
Well, one of them will only let you do outputs between a certain degree in the unit circle.
Oh, yeah,
But you
yeah.
have that cosine to find some of those. I don't know, it's either one or the other, but one of them will only give you an output between +90 and -90.
Yeah,
And that's why you need the other one.
well, yeah, so basically, cosine is going, or let's see, sine is going from 0, let me draw it in red. Sine is going from 0 to 1 here, right? There's your red. Cosine, I hadn't really thought about it this way before, but cosine is going from 0 to 1 in this direction. They're going to crisscross right at 45 degrees and be equal to each other.